Hello everyone, welcome to this video. In this video we shall see application of Lagrange equation and in particular we'll see linear harmonic oscillator. How to calculate the equations of motion for linear harmonic oscillator using the Lagrange equations, which we have derived in the previous video using the Hamilton's variation principle. Now, in order to determine what is the equation of motion for this linear harmonic oscillator, we shall see several general steps which would be useful to obtain the equations of motion. So first of all, an appropriate coordinate system should be selected, and after that we should see what are the constraints and what forces are applicable on the given system. Thereafter, we shall write the kinetic energy T for the system in terms of generalized coordinates. Remember this, whatever generalized coordinates you have selected, you just simplify the expression onto that. Then you calculate this potential energy and then you calculate the corresponding Lagrangian. What is this? This is equal to T minus V. Thereafter, once you have the Lagrangian with you, you can evaluate the partial derivative of this Lagrangian with respect to the generalized coordinate Qj and its derivative. Once you have these two terms, you can just plug these two values into this equation, and then you can simplify the this equation to get a second order differential equation, and you can obtain the desired path, frequency, or the time period. So let us see the case of linear harmonic oscillator. Now here you do not have any information how the system behaves and what are the constraints and how does it look. So the first step is we shall visualize the corresponding process and the materials involved, right? So linear harmonic oscillator, it basically is a spring mass system in which we have assumed that this spring has spring constant K, which is fixed for every spring, and this is some block which has mass of m. So now for this we can define the coordinate system as x-axis in this horizontal direction and y-axis in this vertical direction. Thereby, we can choose the appropriate coordinates as Cartesian coordinates because they are the simplest to work with. In this case, all these things we have to decide by our own. Moreover, we shall study the motion of this system, or we shall derive the equations of motion in one-dimensional motion. That means we'll only study the horizontal motion of the spring. That means this block could either move in this direction or it could move in this direction. So whatever is the displacement over here, it would be represented by the distance x. So next, let us calculate the associated kinetic energy, potential energy, and the Lagrangian. The kinetic energy for most of the systems, it is given by half mv square, and you know what is v? V is the time derivative of x with respect to t. In other words, you can write this as x dot. Dot represents derivative with respect to time t. Therefore, just replace this v by x dot, so we have this thing. So kinetic energy in terms of generalized coordinates, and generalized coordinates here we only have x. Next is calculation of this potential energy. Now potential energy is given by the amount of work done on the system. So the amount of work done by the system would be minus of integration of what is work done, force into displacement over the whole region. So what force is applying onto this? So the only force is the restoring force, which is provided by this spring, and it will pull this mass towards itself, towards this origin, right? Therefore we have a minus sign to it. Therefore the force would be minus k into the corresponding displacement by Hooke's law. So Hooke's law states that the force is directly proportional to the displacement, and we can replace this proportionality sign by introducing this constant k into x. So this is the restoring force present in the spring mass system. So therefore this F could be written as minus kx. So we can integrate this over 0 to x, and so we'll obtain this. We can integrate it over 0 to x, or we can have the indefinite integral and we can apply this constant c of integration. Therefore our V potential becomes kx square by 2 plus c. So the Lagrangian t minus v, it becomes half m x dot square minus of v. This is this thing. So once we obtain the Lagrangian, the next step is to calculate the equation of motion, the Lagrange equation of motion, which is similar to that of Euler-Lagrange equation as we do in calculus of variation. So here we have to first calculate, we have this L, we have to first calculate del L by del x, and then we have to calculate del L by del x dot. Why x? Because now our coordinate system is reduced to Cartesian coordinates, and that too in we are talking about that in one dimension only. So we only have x here. So del L by del x, it would be the partial derivative of this L with respect to x. So we'll assume, in this case we'll assume x dot to be constant. If x dot is constant, this term becomes 0. This term would give you minus kx, and this term being constant, this is also 0. So you have del L by del x as this. In this case, you'll consider the terms containing x to be constant. So this term would give you mx dot, and this term, as it does not contain x dot, it would be 0, and this being constant is also 0. Once you have these terms, you can plug these values onto this equation. You'll get something like this. Now mass being constant, you can take this mass out from this derivative. Now you can differentiate x dot, you will get x double dot, the second derivative of x with respect to time. So this is the second order ordinary differential equation representing the motion of simple harmonic oscillator. So now for simple harmonic motion, the usual equation is x double dot plus omega square x is equal to 0, where x represents the displacement. So basically if there are no frictional forces or the resistive forces, then we say that for spring mass system, if it is in some motion, so it'll go forth and back infinitely for many for a large time period, as there are no dissipative forces acting on it. So this is the equation in ideal case. So this omega, this is known as the angular frequency of the oscillator, and omega is equal to 2 pi nu, where nu is the frequency, and t, which is given by 1 upon nu, this is called the time period of oscillation. This is just a recap of whatever we have done in our previous classes, or as in physics. So for a simple harmonic oscillator, we have obtained this equation, mx double dot plus kx is equal to 0. So in our case, what is omega? Omega comes out to be square root of this quantity. So this is the angular frequency for our given spring mass system, the given simple harmonic oscillator, and time period, it is 1 by nu. And what is nu? 2 pi nu is equal to omega, so nu is equal to omega divided by 2 pi. So it comes out to be this, and omega was square root of k upon m. So this is the time period associated with our system. So let us take another example consisting of this spring mass system. Now the only thing that is given to you is this statement. Rest you have to identify by yourself. Solving Lagrange's equation would be very simple, but reaching out to find correct L, that is the most important step, and to identify what exactly is happening over here. So let us see the statement. This says mass suspended at the end of a light spring. So we have one spring which has spring constant k. So, and a mass is suspended onto it, is set into vertical motion. Now instead of this horizontal motion, we have a vertical motion. So we need to use Lagrange's equation to find the equation of motion for this mass. So now we need to think about all the forces and everything that is working onto it. So you can see this thing. This is a rigid support. A spring is hanging onto it, and some mass m is again attached to the other side of the spring. Now two forces, and this spring has spring constant k. Now two forces can act on this spring. One would pull it down, and this force would be due to gravity, so it would be mg. Another force is due to this spring, and by virtue of its spring constant, it is the restoring force. It would work in the opposite direction, therefore minus k of x, whatever is the displacement. Now talking about displacement, we could have only two cases. This is the system when there is no external force acting on it. That is, we can say the system as a whole is in equilibrium. So we can take this point O as the reference point. So now if the spring is stretched, in that case the mass would be little down, and let us say from this point O, the reference point, it has now it has been now displaced by the unit x, which would be our displacement. Another case would be if you push this mass upwards. That means in this case the spring would contract, and you'll see a displacement in the upward direction by x units again. This is our assumption that it has been moved into x distance. So now according to this, we can calculate the kinetic energy. What would be the kinetic energy T? It is again half mv square, no change in that, so half m x dot square. Now talking about potential energy is the amount of work done during its fall from some point O to the point P where it is now. In this case it is here, in this case it is here, right? So in both the cases we have two forces acting on it. So the potential energy is negative of work done, and what is the work done? It is the amount of force which has been applied to displace the body to a displacement of dx, to a very small displacement dx. So total work would be integrating it from 0 to x. 0 is the reference point, and whatever displacement we have covered, so till there we'll calculate the amount of work done by the system. Now what is this F? Now we have two forces working on our system. One is this downward force, and this force would be mg due to gravity. One is this upward force. This would be due to spring, due to presence of string, which will pull it up. So it would be minus k of x. Therefore the forces would be mg minus kx and dx as such. Now we can integrate this thing. We would get mg into x, limits vary from 0 to x. So it would just be x, and here it would be minus kx square by 2. So you'll get potential energy as this one. Now Lagrange in L would be calculated as T minus V. So we have T, we have V. So you can substitute the values. Now the simple part is there. We have the Lagrangian equation. We just have to calculate the partial derivatives, del L by del x and del L by del x dot, and we just have to substitute it over here. So this is our equation of motion for this system. Well, so this is the equation of motion for the spring mass system. So you got, I think you got a pretty much very clear idea about how to calculate this equation of motion when we have spring mass system. So we can see more applications of Lagrange equation in the next videos. I must say, please practice for various problems, because until and unless you are able to calculate this kinetic energy and this potential energy correctly, you won't be able to tell what is L, and then you won't be able to reach at the correct answer. So do practice more applications of this phenomenon, this topic, Lagrange equation. This is really important, and it is also really interesting. Well, that is it for this video. Thank you for watching.